Now this torque tau equal to P sin theta will rotate the dipole along the field direction, and the amount of work done by this torque will be stored in the dipole as its potential energy. So this will rotate the dipole along the field direction, and it will perform some amount of work for the rotation, and that amount of work done will be stored in the dipole as its potential energy. Okay, so the torque, suppose the dipole at any time the dipole was at an angle theta with the field direction. Okay, makes an angle theta with the field direction. So the torque acting on the dipole at that time is P sin theta. Okay, now the work done to rotate the dipole further by an angle d theta is work done to rotate the dipole further by an angle d theta is tau into d theta. Okay, so what will be the work done to rotate the dipole from an angle theta 1 to theta 2? So the total work done to rotate the dipole from an angle theta 1 to theta 2 is tau d theta, integration theta 1 to theta 2, tau d theta. That is equal to Pe sin theta. This is the magnitude of tau into integration theta 1 to theta 2. So integration sin theta d theta equal to minus cos theta. Okay, so this is equal to Pe cos theta minus Pe cos theta. Now limit theta 1 to theta 2 as the limit was on theta. So theta 1 to theta 2, that is equal to minus Pe sin theta 2, sorry, cos theta 2 minus cos theta 1. So this amount of work done will be stored in the dipole as its potential energy. Now several types of questions are asked from here. That is, what is the work done to rotate the dipole from its most unstable position to its most stable position, from unstable equilibrium to the stable equilibrium position, etc. Okay. So first of all, you have to understand what is the most unstable position for the dipole, and what is the stable equilibrium position, and what is the unstable equilibrium position. So all the positions are unstable positions for the dipole. Okay, except two positions, among which when the dipole makes an angle 90 degree with the field direction, it is at its most unstable position. Okay, so the work done, we have the work done equal to minus Pe cos theta 2 minus cos theta 1. Cos theta 1 was the initial angle and theta 2 was the final angle. Okay, so now what is the most unstable position? Suppose this is the electric field. If the dipole makes an angle 90 degree with the field direction, this is plus q and this is minus q, then maximum torque will act on the dipole. Okay, so this is the most unstable position for the dipole. Now, stable equilibrium position and unstable equilibrium position. For an example, equilibrium means the net force and the net torque on the dipole is 0. Okay, but what is the difference between stable equilibrium position and unstable equilibrium position? If we disturb the unstable equilibrium position, the system will not come back or regain its equilibrium position again. And in case of stable equilibrium, if we disturb the equilibrium position, then the system will come to its equilibrium position again. For an example, suppose we have a container in the shape of U, and we have a ball at the bottom. So this is at the equilibrium position. This is the equilibrium position for the ball in such type of container. Okay, and all the other positions are unstable equilibrium position. You can't keep the ball here without any support, but you can keep the ball at the bottom point. Okay, if you disturb the equilibrium position, the ball will move a little bit, then come to this position again. So this is a stable equilibrium position. If you disturb it again and again, it will come to its equilibrium position at every time. Okay, but think the situation. Suppose the container is placed in this way, and you put the ball here now. It will remain in equilibrium. That is, you can keep the ball here. But if you disturb the ball a little bit, it will never come to this position again. Okay, so this is the unstable equilibrium position. If you disturb the ball, it will go away and never come back to its equilibrium position again. So the forces acting on the ball was balanced somehow. So the total torque acting on the ball is 0. So that's why it is at static equilibrium. But if you disturb the equilibrium position, it will never come back to its equilibrium position again. Is it clear? So in case of dipole, there are two types of equilibrium. One is stable equilibrium and another is unstable equilibrium. So suppose these are the field lines for uniform electric field. If the dipole is placed in this way, the plus q charge here and the minus q charge here, the force acting on the plus q will be q into E in this direction, and minus q into E in this direction. These two forces are equal and opposite, so the total force acting on the dipole is 0. And what is the torque? As the line of action of the two forces are equal, are the same, as the line of action of the two forces are same, so the net torque acting on the dipole is 0. So this is equilibrium position. Total force is 0, total torque is 0, line of action is same, so there is no, the distance between the line of action between the two forces is 0. So the total torque is 0, total force is 0. So this is the equilibrium position. Now, whether it is stable equilibrium or unstable equilibrium, for this we have to think, if we disturb the dipole by some amount, suppose it makes an angle d theta with the field direction. Okay, so what will happen? This is the minus charge, so a force will act in this direction, QE, and the same force will act in this direction, plus QE. Okay, so this will again rotate the dipole along the field direction, and the dipole will come back to its equilibrium position again. Is it clear? It will come to its previous equilibrium position again, because this will rotate the dipole in this way. If you disturb in this direction, QE will act plus QE, this is the direction for minus QE, the dipole will be rotated in this direction. So it will regain its equilibrium position again and again if you disturb the dipole. So this is the stable equilibrium orientation for the dipole. That is, when the dipole makes an angle 0 degree with the field direction. When it makes an angle of 0 degree, that is, the dipole moment and the electric field vectors are parallel to each other, then it is at the stable equilibrium position. The torque is 0, the force is 0. Okay, so this is the stable equilibrium position. Now unstable equilibrium position. Okay. So these are the field lines. Okay. Now the dipole is placed in such a way the minus q charge is here and the plus q charge is here. Minus q charge is here and the plus q charge is here. So the dipole moment, so it is at 180 degree with the field direction. This is the direction of the electric field and this is the direction of the dipole moment. Is it clear? Okay. Now, what happens? The force on plus q charge, the plus q will experience a force in this direction and minus q will experience the same amount of force in the opposite direction. Okay, so the net force on the dipole is 0. Plus QE and minus QE, they will cancel each other, so the net force on the dipole is 0. Again, these two equal and opposite forces acts along the same line. So the line joining between the two forces is 0. The distance between the line joining between the two forces is 0. They act along the same line. So the torque is 0. So the net force is 0. The torque is 0. So this is also equilibrium position. Okay. But what happens if the dipole is rotated by, if it is disturbed from its equilibrium position by some angle? Okay, then this is the plus q charge, so it will experience a force in this direction, plus QE along the field direction, and the minus q charge will experience a force minus QE in this direction. So it wants to rotate in this direction and this one to rotate it in this direction. In the previous case, both the forces tries to move the dipole along the field direction. In this case they are trying to rotate the dipole just in the opposite direction. Okay, so the dipole will never come back to its original position. Okay, so it will rotate and it will be rotated and comes to its stable equilibrium position, from unstable equilibrium position to the stable equilibrium position. So what is the unstable equilibrium position? When the dipole makes an angle of 180 degree with the field direction. So is it clear? Okay, now the questions are very simple. If you understand all these positions clearly. Now what is the work done? So this amount of energy, you may write it as U, potential energy. This amount of energy will be stored in the dipole as its potential energy, the amount of work done. So what is the work done to rotate the dipole from most unstable position, that is theta equal to 90 degree, case 1. Most unstable position, that is theta 1 equal to 90 degree, to most stable position, that is to stable equilibrium, that is theta 2 equal to 0 degree. So the work done is W equal to PE cos cos 0 minus cos 90. So this is minus PE. This is 0, this is 1. Okay. So this is minus PE. Now what is the work done to rotate the dipole from unstable equilibrium to stable equilibrium? Unstable equilibrium means theta 1 equal to 180 degree and theta 2 equal to 0 degree. Unstable equilibrium position, this is the stable equilibrium position, and the work done is minus PE cos theta 2, that is 0, minus cos 180 degree. So this is equal to minus PE, 1 minus of minus 1, 2 PE. In general, to rotate the dipole at an angle theta from its unstable position, the work done is given by to rotate the dipole from its most unstable position to an angle theta, to any arbitrary angle theta is, so theta 1 equal to 90 degree and theta 2 equal to theta. Okay, then what is the work done? W equal to minus PE cos theta minus cos 90. Cos 90 equal to 0, so this is equal to minus PE cos theta. So that is equal to minus P dot E. So this is the work done. So this is the amount of energy, potential energy stored in the dipole when it is placed in external electric field. So that's all about the electric dipole.